Hello and welcome to the channel. Here is a cute little equation involving 4 factorials, presented at Canadian Math Competition in 1983. You know, of course, that n factorial is a product of first n positive integers. In particular, 1 factorial is 1, and 0 factorial is also defined as 1. However, the authors of the problem wanted x, y, z, and u to be positive integers. So let them be positive, like I hope all the viewers of this channel. Next come 2 factorial, which is 2, and 3 factorial, which is 6. The first thing we can notice that x, y, and z enter symmetrically into the equation. Therefore, without loss of generality, we can assume that they go in a non-decreasing order. Then we write that x is no less than 1, and so are y and z, of course. And we are going to extend the inequality even further. Let's rewrite the given equation for u, where we can replace x and y with 1 using more or equal sign. Since 1 factorial is 1, the right hand side is actually 2 plus z factorial, which is greater than z factorial, while u factorial can be greater than z factorial only if u is greater than z. So we can extend the inequality for x, y, and z by adding less than u. Now to the real stuff. Since y is no less than x, y factorial contains all the factors of x factorial and maybe some additional factors. Whether or not the additional factors exist, we can certainly say that y factorial is divisible by x factorial. And since z and u are also no less than x, z factorial and u factorial are also divisible by x factorial. Therefore, we can divide our equation by x factorial and get the new equation where all the terms are still integers. And here's your chance to continue. Suppose y is strictly more than x. Then y factorial, in addition to x factorial terms, has at least x plus 1. When we divide y factorial by x factorial, the first x terms go, but x plus 1 stays. This means that y factorial over x factorial is divisible by x plus 1. Since z and u are no less than y, they are strictly more than x. Therefore, in the similar way, z factorial over x factorial and u factorial over x factorial are divisible by x plus 1. We see the 3 terms in the equation are divisible by x plus 1. Therefore, the remaining term, which is 1, must be also divisible by x plus 1. However, since x is at least 1, then x plus 1 is no less than 2. This means that no matter how desperately we may wish it, 1 cannot be divisible by x plus 1. This contradiction eliminates the chance of y to be strictly more than x. And since y cannot be less than x, y must be equal to x. So the second term of the equation is also 1. The equation gets simpler. And now the attention is to z and to you, because this is another chance of yours to continue on your own. We already know that if z is strictly more than x, then both z factorial over x factorial and u factorial over x factorial are divisible by x plus 1. Since 2 terms in the equation are divisible by x plus 1, the remaining term, which is now 2, must be also divisible by x plus 1. In this case, 2 must be no less than x plus 1, so x must be no more than 1. Since x cannot be less than 1, it must be 1. In this case, both denominators in the equation become equal to 1, so the equation can be rewritten as u factorial equals 2 plus z factorial. We can notice that if z is 3 or more, then u is also no less than 3. In fact, u is even greater than 3, but it doesn't matter much. What really matters is that in this case, both z factorial and u factorial are divisible by 3, while 2 isn't. This means that z must be less than 3, and since z is more than x, which is 1, z is greater than 1. The inequality for z shows that z can be only 2. Substituting 2 for z into the equation gives u factorial equals 4. Can we get the value for u? We see that 2 factorial is 2, while 3 factorial is already 6. So the following factorial values will be greater than 6. Therefore, the equation u factorial equals 4 has no solutions. That shows that z cannot be strictly more than x. And it cannot be less than x either. Therefore, z must be equal to x and y along with it. This means that our equation has another term equal to 1, and the left-hand side of it is just 3. The new equation can be rewritten as u factorial equals 3 times x factorial, and the rest is really easy. Since 3 is a prime number, it can only be a whole factor for u factorial. And 3 must be more than x, as all the factors not exceeding x belong to x factorial. Therefore, 3 is the greatest factor for u factorial, which simply means that u equals 3. Then x must be 2, in which case y and z will be 2 as well. And this is how the equation looks like after the substitution. It is correct, and this is not yet the end. Because in addition, I'm going to present the official solution from the authors of the problem, which is much shorter and much trickier than my own. Again, we use the inequality for x, y, z and u, but this time the strict inequality between z and u is really essential. It allows to write that z is no more than u minus 1. And here comes the magic trick. We write u times z factorial is no more than u times u minus 1 factorial, while u times u minus 1 factorial is just u factorial. According to the equation, u factorial is x factorial plus y factorial plus z factorial. And since x and y are no more than z, the expression is no more than 3 times z factorial. This chain of equalities and inequalities results in the following inequality. U times z factorial is no more than 3 times z factorial. And after dividing by z factorial, we get u is no more than 3. Now you can appreciate the magic of the trick, which has left us with only 3 values of u. Now we can check each value of u and find which one suits. However, since we started being tricky, let's be tricky all the way. How can we avoid checking all possible values of u? So we have u factorial equals x factorial plus y factorial plus z factorial, and since each factorial in the right hand side is no less than 1, u factorial is no less than 3. However, 2 factorial is only 2. Therefore, in order u factorial to be no less than 3, the value of u must be no less than 3. And combining the inequalities for u gives u equals 3. In this case, z is no more than 2. And x and y are also no more than 2. This means that x, y, or z can be either 1 or 2. Can we avoid testing all possible triplets of x, y, and z? Yes, we can. We just point out that the maximum value of the left-hand side of the given equation can be reached only if x, y, and z are all equal to 2, while the value of the right-hand side is over 6 and does not depend on the values of x, y, and z. When x, y, and z are all equal to 2, the left-hand side equals 6 and matches the right-hand side, providing the solution of the equation. While if at least one of x, y, or z is less than 2, the value of the left-hand side is less than 6 and doesn't match the right-hand side. And we get the same solution as before and the familiar identity. And this is just the final remark. If we extend the domain to non-negative values, in other words, allow a value to be 0, will that bring additional solutions? The answer is no, for a very simple reason. Since 0 factorial equals 1 factorial, any 0 in a solution could be replaced by 1. However, in the only solution we obtained, value 1 never appears, which means that the requirement of x, y, z, and u to be positive is actually redundant. And this is the end.